So, welcome back, everybody. And what we are going to do today is actually to have a quick, small session now, 10-15 minutes, where I'm going to give some hints and tips about solving the exercises this week, because there are some small things which are worth paying attention to, and in particular about the numerical exercise. And then, if you remember back what we did on Wednesday, I gave you two exercises. So how many of you were able to solve both exercises? The two examples which we had on Wednesday. Okay, so because I could see that when it came to the second one, there was quite a disappointment in your eyes that you were just waiting for the answer. So let's try to go through that one, especially with this kind of Coulomb forces. And the reason why I bring these things in now is because this course, if you think a little bit about it, is very much about bringing many of the dots together. So there is lots of mathematics which you've seen before. Many of you have taken CMSE 201, and we want to link mathematics and the computing you've seen in CMSE 201 with physics. So to bring all these elements together, it takes often some time. So the first things which I'm going to do today is actually try to bring some of these dots together. And there is an element in the numerical exercise which we often tend to forget. And you will see that the solution will actually depend on us not having forgotten about the numerical method which we are using and the parameters of the numerical method. So there are some small things which are easy to forget and which belong to this kind of thing of bringing many of these small things together, so that this course is actually a course which attempts at making a unity of computations, mathematics, and analyzing of physics and solving of physics problems. So slowly, I hope, I'm hoping that you can follow us along this path, because that's what's going to lead you to this, the excitement of doing physics, when we can bring all these things together. So let me first bring up the solution to this example 2 here, and just go through it, because that contains some of the mathematics which we may have forgotten, and which is extremely useful in this course, when we analyze forces and potentials. So I just want to give you this kind of small hints and tips, so that we can hopefully attack the exercises which are to come in a perhaps easier way. So let me just go through that example which we had on Wednesday, and let's switch over to the whiteboard. So the example I'm thinking of is actually example 2 here. And we had an example of a force, and we had to calculate the curl. The first example, the curl is automatically equal to 0, because we're just in one dimension. And the curl relies on you having a plane which you can span with 2 vectors, and you have a vector perpendicular to that plane. When you're just in one dimension, then it's automatically 0, the curl. But let's look at the second one, because the second one is related to the gravitational force or to the Coulomb force, and many of the forms which fundamental laws of physics take. So taking the derivatives here is a useful exercise. It's not the most exciting thing we're going to do, but it's useful to have seen it. Okay? So let me just go through the details, so you can actually see how we actually can show that that is an energy conserving force. It's a conservative force. So I'm going to actually not start with the, so this is this example 2 here, and let's switch over to the whiteboard, so we can look at that one. So if we start, instead of starting with the potential, with the force, we start with the potential. And the potential depends only on a scalar. And let's write this potential like a parameter gamma of 1 divided by r. So if we have the gravitational force, then this gamma is nothing but the gravitational constant, the mass of one object, and the mass of the second object. And R is actually the absolute value. This is the magnitude of the distance between the two particles or the two objects squared plus x plus y1 minus y2 squared. And then there is a just continuous here. And if we are in 3 dimensions, this is C1 minus C2 squared. So this is the expression for the potential. Now let's simply look at this as a function of R. Okay, so we forget about that. This is something which depends on the relative distance. So we have learned that the force is now given by the gradient of the potential. So let's do that first, and then we calculate the curl. So if we write this out, this is the same as this minus gamma, this constant. Actually, if we have the a Coulomb force, then this is given by the charge of particle 1, charge of particle 2, divided by 4 pi, and the permittivity in vacuum. In that case, if you just change gamma, you have another potential, which now in this case will be the electrostatic Coulomb potential. So this will be given by dx. So just to remind you of some of the mathematics which you have seen before with the gradient. And this is dy, and then we have the direction, the unit vector in the y direction. And then we finally have z. And this is then multiplied or taking the derivative of 1 over r, where we now write simply 1 over r as 1 over square root of x squared plus y squared plus c squared. Okay? So if I take the derivative with respect to x of this quantity, which we have here, 1 over x squared plus y squared plus c squared. If we do that, what we get then, we get 2x, so 2 divided by x, and then we have 2 because we have a factor 1 over half for the square root from the square root. And this comes like x squared plus y squared plus c squared to the power of 3/2. And when we rewrite it, this is the same as x divided by r, this quantity, to the power of 3. Does that sound reasonable, guys? So you would see the same if you take the y direction and the c direction. So you would basically get the same. So if I do the derivative with respect to y and c, so if I take dy of the same expression, 1 over r, what we're going to get then is y divided by r cubed. And then I have dz of 1 over r, which is equal to z divided by r cubed. And then I can bring everything together. And if I bring everything together here, you see now that I have a vector here. So the potential is a scalar, just a number. Now I have a vector here since I'm taking the gradient. So I need to plug in these quantities. So that means that what I get then is that f of r, in this specific case, is equal to minus, and then I have this constant gamma, and then I'm getting x times I plus y times j plus c times k divided by r cubed. And this is nothing but the vector r divided by r cubed. And we can rewrite this quantity as minus gamma. And then I can have 1 over r squared multiplied with the unit vector, which I write like this with a hat on top of it. So this is now a normalized quantity, which is just r divided with its absolute value. Sorry, that was not a very nicely drawn r here. Like this. Are you familiar with this kind of notation? So it rings a bell, right? So this is the way we are going to play around in this course. Sometimes we have the potential energy. Sometimes we have the force, and you will be asked to find the potential energy with force. So if I give you an expression for the force, and this is about exercise 5, if you have the force and you ask, find the potential, which theorem would you use then to find the potential? So this is a hint about exercise 5, where you actually have an expression for the force and you ask to find the potential. So we had it last week, begins with W. Yeah, the work energy theorem. So if somebody gives you the force, then you can use the work energy theorem to find the potential. If somebody gives you the potential and you're asked what is the force, then you will take the gradient of the potential and then you have the force. So these are the kind of simple recipes which you can use when you want to find these specific quantities. And often you will find measurements of the force. That means that you can, if you have measurements, you can parameterize it in some mathematical form. And if somebody gives you a mathematical form for the forces, then you can integrate up with the work energy theorem and find the potential. And as we will see next week with the potential energy, we can make a lot of intuition about the system here. Okay, so let me calculate the curl now, because now we have the force, and we're going to use this expression to find the curl. And this is another kind of exercise which we often end up with having to do when we do mechanics or physics in general. So now we want to find this quantity here. And this quantity is now given if we now write out the different components. So this is going to have a dy fz minus d dz of fy. And this is the x component. And then I have plus, and then I have a d, and then I have a dz of fx minus d dx of fz multiplied with j plus of d of dx of f of y minus d dy of f of x multiplied with the unit vector in the z direction. So what I'm going to do now is simply to take this first term, because we don't need to do the other ones, because when you've seen that term, the other ones just follow. So it's just a matter of taking derivatives, and taking derivatives is not the most exciting thing we do, right? When you've done it once, you've done it once. And there is no deeper insight if we calculate derivatives up and down here. So let's now look at the term, which is dy of f of c here. So this is the same as us having to calculate this term here of d dy. And the z component is given by z divided by x squared plus y squared plus c squared to the power of 3/2. So when I calculate the derivative here, what this is going to give me is minus gamma, and then I have 3 divided by 2 here. There's going to be a factor of 2 times y, and then it's multiplied with z, and this is divided by x squared plus y squared plus c squared to the power of 5/2. And I can simplify, so I get minus gamma times 3 times y times z, and I have my r, which is now given, well, let me just write it out in terms of x squared here. So we just x squared, y squared, etc. So I have x squared plus y squared plus c squared to the 5/2. The next term I need to look at is now dc of f of y. And that's going to be equal to minus gamma of d dc. And then I have the y component, which is simply y, divided by x squared plus y squared plus c squared to the power of 3/2. And when I take the derivative here, what I get is, again, I'm going to get minus gamma times 3 times y times c divided by x squared plus y squared plus c squared of 5/2. And when I then bring together d dy of fc minus d dc of f of y, this is the x component of the force. You see now that I have two terms which are just equal, and they cancel each other. So that means that this is equal to 0. And if you repeat this exercise for the other components, the j component and the k component, you will get 0 as well. So I hope you don't get offended if I don't do all the derivatives. But you see the basic pattern here, right? So this means that this type of forces are conservative forces. The curl is 0. So if somebody gives you the force, you can find the potential by using the work energy theorem. If you have the potential, you can find the forces. And if you have the forces, then you can find the acceleration. And then you can solve the equations. So this was about connecting one of the dots, the mathematics, with the kind of physics we want to do. And now it's about the numerics and the physics we want to do. So let's take a look at the numerical exercise, this exercise 6, and look at some of the results which we can get. And let me see if I can have you to think of what is going on here. So I'm going to show you the Jupyter notebook for this specific exercise. So I'm going to shrink down a little bit the fonts so we can squeeze it into a screen like this. Can everybody see properly in the audience here? Can you see well? Now, if you now look at what I've done here, I've chosen a time step, delta t. So I'm using, so in the discussions here, what I want you to have you with me on is that we are using Euler's method. So Euler's method is a approximation to the true problem. We have used a Taylor expansion and we stop at the first derivative. And then we get a recipe for finding positions and velocities, okay? And delta t is a parameter which we choose. So what I'm saying now is the root of all evil you're going to see here, okay? So let us run the calculations. So I'm having a ball which has a radius of 0.1 meter. So when the object comes to rest, we should have a height which is 0.1. So if I run the simulation now and look at the value of y as a function of time, when it comes to rest, then the height should be equal to the radius of the ball, right? Times 2, obviously. Okay? So let's look at the simulation now and just run it as it stands. So now it contains the gravitational force, the normal force, and it contains also the air resistance. So let's just run it as it stands here. And this is what we see. That doesn't look like as 0.2 meters, right? As it comes to rest. Would you agree on that? So something is wrong. It behaves as we want. You can see now it bounces up and down. So every time it hits the ground, there is a normal force, which we approximated with a spring force. So it jumps up again, comes down, and then there's air resistance. So slowly it comes to rest. So any good ideas? So here we are going to connect the dots. And the thing is that when you're solving the exercises, it's often, I mean, I was like that. We often disconnect things. So we want to solve a physics problem, and then we think about the physics, and we forget that there is a numerical component. or a mathematical component, and we tend to forget about it. So if you look at this result here, let me change this parameter delta t, okay? So I'm going to change delta t here, and I'm going to say now that delta t, I just make it larger because I don't want to run so many cycles. I just make it 10 to the minus 2. Let's see what happens then. Wow, this is not good, eh? So the reason why I bring this up, so I have this bad tendency, since I'm a computational physicist, to give the kind of impression that if you can compute, you can solve all problems. But you should always think of these as approximations to the true equations. So the approximations come with parameters. Delta t is a parameter. And what you're seeing now is that Euler's method is not the best method. So next week, when we are going to look at the Earth-Sun problem, you will see that Euler's method doesn't conserve energy, which is really bad. And at a certain point, the Earth is going to leave its orbit. And you won't have a solar system which is stable. So take always these methods. You have to be critical and you have to know what are the limitations. So Euler's method is easy to implement, but it doesn't conserve energy, for instance. So if I now decrease this time step, you're going to see that I'm going to get better and better results. So let's do that. And next week, in connection with homework number 5, we are going to look at methods which are better than Euler's method and which imply just a simple small change. So let's make this 0.01, just make it smaller. Aha, now it looks reasonable, doesn't it? So if you look at the height here, now it's going to look like the radius of the ball times 2. So this looks like as it's come to rest. So the problem is simply the usage of a specific method with a specific time step. So the time step is a parameter. And when we often solve this type of problems, we are so eager to get the physics right that sometimes we tend to forget about some of these technicalities. But just keep this in mind. And if I tend to overemphasize the numerics, you should always be critical, right? I'm like a car seller, right, who wants to push the methods. But actually, numerical method allows us to solve these problems much easier than by paper and pencil. Next week, and this is where I'm going to end now, next week, we are going to encounter something which is a simple modification of Euler's method. Have you heard of Euler-Kromer's method? This is just a simple thing you can do in your calculations by just using the updated velocity in the calculation of the position. And next week, we are going to see this implemented for the Earth-Sun problem. So the only thing I need to do is to use this velocity, which I found here, in the calculation of the position. And now I can go back to this worse time step, which I have. And if I run that one, looks beautiful, as it should. So the reason why I brought these things up, these are kind of small things which are easy to forget about, but which also link the dots between the physics we want to do and the tools which we have, mathematics or computational tools. And this is where I'm going to stop now, so we can have time to solve exercises. So Shu Yu is also here, and Abby comes around 4. So we should have enough people to chat with you folks about the exercises. The recording is obviously going to be online, so if you want to revisit these things, feel free to do that. Okay? Okay, I'm going to stop the recording. And for those of you online, feel free to ask questions via the chat. So I'm going to stop the recording for those of you online. And Shu Zhu is also following the people online. And I will try more to jump around in the audience and then hopefully also answer your questions